second part of today's lecture, we will continue to study the assembly language, okay? And I will show you how the high-level language statement can be compiled and consists of several instructions, okay? So you know the relationship, because now it's a conclusion of the study of instruction of a processor, right? So let's put everything together to see how it works. The previous lecture, we talked about how instruction are used to perform expression and how to get the data from to and from register and memory and access the chunk of data and doing some very simple loop or make decision. Okay, so the rest is having to think more, and then we study this and then continue to compose everything together. So it's a function call and the use of the stack to pass parameter. Okay, a function or in a program is a kind of abstraction of the commonly used part, okay, which is abstraction is the most powerful tools or in almost any study in science subject. Okay, so we probably think of software in terms of a function more than anything else. This way of solving large problem, we call divided large problem into smaller one, so we can solve smaller case. And the idea is an abstraction. Okay, when you want to run a program and call another function, right? At the end of the function, you want to return back to the program that called it. So there have to be somewhere to store the return address. Okay, the instruction that we use in our processor called jump and link. To do a jump, we need one argument to tell where to jump to, so we call that address. And the other argument is where we put the return address. So because we have to give it one register, okay. And when the end of the function we want to return, we use the same register, okay, right? Because the return address is stored in this register, so we execute the instruction return and then give it the return address in that register, so it can return to continue where it comes from. This register is called link register. Okay. In function call is how to one is where a local variable, because once the function finish, then we have to restore what we use. Say local variable are usually register. However, the program that call us also use the register, right? We don't know which register they use. We know as our function, we know which register we use. So you say I use 3 register, 1 to 3. So once they jump to my function, I want to use 1 to 3. So I have to save 1 2 3 before I use it, because this 1 2 3 may be used by the program who call me. Once I finish my work, then I can restore this 1 2 3 of the caller. Okay, that's first thing. The second thing is, if the caller pass some parameter to us, like a function double. I want to double 10, then I want result to be 20. Then number 10 must be sent to the function. Okay, we send that through the stack. So we push it to the stack, which are a chunk of memory in the main memory. But between the main program and the function, they have to know where the stack. We use the stack pointer as the to point to the location that we want to use as a stack. So there must be at least one register to be used as a stack pointer. To instruction is necessary to push the value to the stack or to get the value from the by popping them. Both instructions used to register. One is the stack pointer, and the other one is the value we want to push to the stack, or the value that we want to keep popping from the stack. And to know where we save and restore register, we use another pointer we call frame pointer to point to that place. So when function is called, and let's assume this function want to use to register, then the first thing we do in the body of the function is to save this to register by pushing them to the frame. Okay, and then we do something that we want to do, and then we restore them by popping them from the frame. Okay, because the value in the frame is ordering reverse when we create them, and then when we save them, we push reserve 1 and then register 2. Therefore, when we restore them, we pop, then we got register 2 first and then register 1. Therefore, the order must be reversed in the stack. Let's show you the example. This is a pseudocode. The main program want to do a double, right? 10 and then print it out. So the double is a function. It receives one number and then double that number and return it. Okay, how we write it in assembly? Let's say we y. Okay, in this one we use register 1. Okay, and the other register we use a symbolic name. Okay, I show you how to write assembly language to have symbolic name later on. We want to send one number to the function. So we push that to the stack, okay? And then we jump to that function called number, double, and use this return address register, okay? Which exactly what register it is can be defined later on. Then as a convention, the return value, the function want to return a value, it will be kept in one register. We call that return value register. So we get once the double return, so we move that value to y, and then they print it out, and then we stop. In the function, this function want to use one register, right? So we have to save the register to the frame, right, using frame pointer. And then next is we get the parameter that sent to us, that number 10. Okay, so we pop it out from the stack. So there are two chunks of memory. One is the frame that used to keep the register. The other is stack that used to pass parameter, okay, to the function. So we pop that out. So we get the value x on number 10 in the example, and then we add together and keep that in one register we call return value, and then we restore the register and return. And this is how we write the symbol. We use a frame pointer, stack pointer, return value, and return address as the register. So we write frame pointer is register number 27, stack pointer register number 28, and so on. Okay. you can you don't have to use symbol. You can write frame pointer as R27 by yourself. As a convention, we use a high number register as this global register. Okay, because this cannot be used by something else throughout the whole program, because it is used for managing this memory. Before we use the stack or a frame, we have to say where it is. So we have to set the initial value to frame pointer and stack pointer. In this case, we use the memory at the frame as 1000 and the stack at 2000. So actual program, this first section, this is a new to us, the symbolic section. So defines symbol name. Second is now starting to do coding. The main function is like this. Oh, right. This is 10. So we initialize both stack and frame, and then move number 10 by pushing it to the stack and call double using return address register, okay, a link register. And once it return, we get the value in return value register, and then we move to y to our local variable and print it out, and then stop. In the function double, we save the register that we want to work, to use, and then we pop the passing value that's sent to us, and then use that value to calculate in the body of function, and keep the result that we want to return in a register called return value, and then restore register that we use and return. Okay, download the tools and unzip it. You have this sort of directory structure. We have the first directory is the assembler that we already familiar with, and the simulator that we familiar with. Then today we include the compiler here, and all the program will be in the test directory. Okay, so this is where we are right now at the test directory. And let's see, our program we call fun1. So this is a program that I just showed you. So this is in assembly, so we assemble it. And see if there is any error by see the listing. Look okay to me. Okay, there's no error message here. So we can run it. By executing the object file. Okay, let's go to step by step. First of all, we trace one step. Okay, this is initialize the frame pointer and stack pointer. Okay, let's see the memory there. We have this is where we have the frame, should be all 0. Okay, this is where we have our stack. Okay, so seem okay, and you can see the number here. Let me enlarge it. Okay, right, that the frame pointer and stack pointer contain the correct initial value. Next is we step again. Right, this is number 11. So we send to number 11 to the function double. All right, and we push it to the stack. Okay, stack is at the 2000. So let's see, is it there? Okay, you can see that the 2001 already got one number there. So this is why we push the value. Next is we call subroutine, right? So we jump to double, which is the instruction at the location number 8 and use R30 as the link register. Therefore, R30 now will store the return address. Now we add the program counter number address 4. So when we return, we want to continue with instruction at the address 5. Therefore, register 30 should have the return address, right? 5 here, as we expect. So all is good. Now we are in the body of function double. The first instruction is to save the register, okay, that we want to use. Okay, and we pop the passing parameter from the stack. Okay, we now we have the number 11 in the our local variable, and then we add it, right, and keep it in return register, which is number 29. Now the correct result double 11 is 22. Then we restore the register 1. Unfortunately, but it's the same number. Okay, and then we return. Okay, the next instruction should be instruction where we return to. So now we are at 11 and we want to return to 5. Okay, next instruction will be 5. Okay, and we move the return value that's stored in register number 29. Okay, and print it out. Okay, so you can see the number print out on the left on the screen, and then stop. Okay, so we execute exactly 13 instruction. All right. So if we want to go it again in one go, we just use go. Boom. Okay, so so that's the last part of explaining how to use instruction. Now we can do function call properly with passing parameter. Okay, let's see. Okay, so I think the syntax is correct now. Okay, right? Look okay. So I keep it into, I will distinguish the assembly language by -s. Okay. And let's see what it look like. So let's see the main program first. There's a lot of things, but the main body is here, right? So we remember we move a 1, right? A equal 1, B equal 2, and add together. Okay. And in order to make sense, we have to print something, right? Let's say print C. I hope that it is correct. Boom. And let's see again. Add to us. Oh yeah. So the print has been translated into trap properly, trap number 1. So we can run this program to see if now we have the correct assembly language. We have to assemble it. Okay, and we type to see, should be okay because it's compiled from compiler. Okay, look okay. So we run it by running simulator and to S object. Okay, and we go at 1, boom. Okay, so 1 plus 2 equal 3 as usual. Print y. Hopefully, save as double. And then we compile it. Okay, let's see by our eye. Okay, look okay. Therefore, we keep it in double S. Have a look at this assembly file double S. First, we try to identify part of the assembly that correspond to the part of the high level. All right. Double. Okay. We should start at main. I think main is easier. Main is here, right? There's a lot of mumbo jumbo, so we start with the y equal double 10. So we move 10 to y, push that value, call double, and move the return value to y, okay, and print it. Okay, so this is trap 1 correspond to print y. Okay, and let's see the double. Okay, now my computer, let's see the main part first. It is here. Okay, so we add two numbers together here. So how we get this number? Remember that it had been pushed here. So we pop that value that passed from the caller here, and then use it. And then we move. We want to return this value, so we move to register called return value, right? And this is just superfluous. There's no meaning. Okay, let's see how we handle how we handle the frame. In the compiler, the frame is a bit have a bit more structure. Okay, here we have frame pointer, and we use we store two register, right? R1 and R2, because the main program, which is only this two line, we use two register, right? You can see we use a register R1 and R2. Therefore, before we execute, we store those two registers to the frame pointer. Previous example, we just use push, but this compiler generates a kind of storing into a block of memory. I will draw the picture to you later, and then adjust the frame pointer, and then also we keep in that frame the return address. Okay, remember that we use offset 1, offset 2, and offset 0 in this frame. So now I will draw what that frame look like for you to see. Number 1 is frame pointer, right? Register 1, register 2, and return address. Okay. So let's come back to our, this is register 1, register 2, and then return address. Okay, so this is how the frame look when the program run. You can see that it do the reverse. Okay, the add frame pointer is it just to adjust the frame pointer to go beyond the current frame. Okay, and it will restore the frame again. All right, in the reverse order, and then return to the caller. To make sure that is good, let's say I put it in 33. Okay, now we are writing in high-level language, right? And then repeat. Ooh, we have to quit this one. Repeat the step. Okay, we compile it, assemble it, run it, go, boom. Okay, so the answer is 66 as expected. So let's call it WH1. Okay. Save. Okay, and then we compile it. WH1. See if any wrong. It should be okay. So WH1S. assemble h1s text. Oop. And then run it. It's object code. We go at once, boom. Okay, so it kind of worked properly. So let's see what the assembly look like. So we want to study that. Okay. WH1S. Let's see our main program. Right. So the first line is I equals 0 is here. Boom. Right. And then it jump in the body of the loop here. The body of the loop is the test of I less than 5. Okay. Right. And if it's true, it loop, right, to label 103. So the loop is here. Right. So the main loop is here. So it tests it less than 5, and then if it's true, it jump here. If it's not true, then it fall out of the loop or exists. In the loop, what does it do? Print, okay, and then increase the pointer. Okay, you can see quite clearly here. I want you to be able to identify what is correspond between the high-level language and instruction. Of course, there's this kind of superfluous, right? We have to manage the frame, but you don't have to worry too much about that. Okay, because I saw that the code is not what I expect, and repeat. Should work the same. Now we can see the correspondence between this and this. Okay, this should be the correct version. Now, the first line here, you can see that we use the displacement address to use AX, because AX is small, so it can be put in displacement, and AX have been use a symbol. Okay, it's start at 1100. Okay, so you can see it end by storing and storing. Okay, and R3 is different each time. It's 1 and 2. Okay, and this one is interesting. How we get the data from array and then manipulate it and then store it back. So let's see how. First, before we do that, we have to get the data on the right hand side. Let's see where the index is here. So we use the R1 as an index. Okay, therefore we get the data here, right? And keep the value here, and then add 2, which is this part, and then store here. Okay, so this 3 line correspond to this line. Okay, right? So you can see the essential. And we print here. Okay. And the last in the loop is to increment the index. The rest is not interesting. Okay, this is housekeeping. I think that's all that I want to show you today. And within this page, the first line is the compiler in browser. It is written by one of my master degree students many years ago. So let's see, does it work? Okay, but you don't have to install any program, right? And you can do it on the browser. Okay, because it is written in JavaScript. So I think this probably solved. Okay, then you recompile again. Okay, so no error now. This will not run, it just compile. Okay, so I think it used the same compiler, you can see. Right, look very familiar. So, okay, so these are like 2 and 3, and then add them together and move to A, and then print A. Okay, so these 1, 2, 3, 4, 5 line correspond to the source code here.